Hello, fellow engineers. Welcome to Coding with Alxor. In the first part of this two-episode series, we're focusing on solving the block optimization problem on the whiteboard, and this one will write the Rust code. Let's get right into it. As we can see on the whiteboard, so mainly we have to implement a couple of functions. So we have the main block. We didn't define yet how we'll call this function. No issues at all. We'll find it out during the Rust code writing down. We have outlined the algorithm, so we have to find out the right side of the solution and the left side of the solution, find a minimal local of between these two. Also, we outline how we'll mark our data structures. So we expect requirements to be a vector of U8, like in our case, if every requirement is enabled, so we'll have 111s for school, gym, and mall. For the blocks, we'll have a vector of vectors of 1 and 0, so or flags which are enabled or disabled. So in this case, on the block 0, if you recall, we have 1 for the school, and for the gym and mall, we have zeros. Okay. Let's get into writing the Rust code. So I've decided to use a dark background for writing the Rust code. But anyway, I think it will be nice in the end. So here what we have our definition of the problem. We saw that in our last episode. Let's close it down for now. I've decided to call the main function optimize blocks. So for now, this will be our entry point. And also I've defined a testing module to be able to call our function. We don't have anything yet defined. I know already what will be the input parameters, and I've defined, let's say, our blocks, the inputs and our requirements, and we have an expected output. So this will be free. In our case, this will be the expected block. Okay, so let's get into it. So first of all, let's define our blocks. So this will be a vector of vectors of U8. Second parameter will be requirements, which will be a vector of U8. You have the usize part. So if you recall the main algorithm, we need to define the solutions. So we'll have mutable solutions. In Rust, we need to mark every variable as mutable if the variable will be mutated. So this is important in our case as well. So this will be a vector of vectors of U32, because I assume we may have a lot of data and we may get a bunch of, let's say, distances between blocks. So we initialize our vector with empty, so nothing yet important. So let's get right into. So if you recall, we need to pretty much iterate throughout all the blocks and compute the local solution. So let's write a code for that. So I guess we'll have an index. We'll start at 0 and we will move into the block's length. So there are multiple ways to do that in Rust. So we can use iterator. So Rust has very powerful iterators. We'll use them extensively in this part of the code, but a little bit later on. So we'll have all of our blocks. Now let's get our solution. So we'll have our solution. We need to compute the solution for each block. So we'll pass down, I guess, the index, we'll pass down the blocks, and we'll pass down the requirements. In Rust is a little bit tricky, and there is a moment to understand, because if we'll pass, let's say, the value not by reference, this will be called a move. And you can use it only once, so you cannot iterate it multiple times. So usually a better solution for these cases, if we don't mutate data. So for example, in this case, we don't mutate blocks and requirements, we can pass them by reference. So this will be a small optimization which we'll need to do. So we have our compute solution. Next, we can add the solution in our array of solutions. And finally, we need to find the minimum solution. So we'll write down a function that will calculate the mean solution from the list of possible solutions. So we'll pass here our solutions. So this is the algorithm outline exactly as on our whiteboard. Now we need to kind of implement the details of each function. You can do that pretty optimally. We can generate a compute solution function, so it automatically generated it for us. So that's a pretty cool feature of VS Code. Here, what do we have here? We have a mismatch. Not sure why it decided to go like that. I guess let's go back U8 and pass it by reference, and here we'll have a vector of U32, that's fine, and requirements, it's a vector of U8, that's also fine. Okay, so we have defined this one. For Rust code to compile, I guess what we can do is just return a simple vector, because at least we want it to compile at first. And what we can work next is on this find mean solution. So yeah, we'll do the same thing. We'll find the minimum solution. Here, to write the code, what we'll need to do. So imagine the following: we'll receive back a list of data, like for example 1, 0, 4. So if you remember the whiteboard part, we computed this manually. So the solution for the first block will be 1, 0, 4. For the second block, I don't recall. Let me fastly open the elements, but actually we don't care. So we'll receive here multiple solutions. So what we'll need actually to find out is the maximum in each block, and in the end to find the minimum out of them. So in order to do that, first thing, I guess, let's define a variable. So we'll have a mutable variable called mean solution. Yeah, so we'll have the mean solution part as well, but it's important for us, we need to find as well the position of that solution. So probably we should call it mean position. I don't know, let it be like that. So to start, we'll create a tuple. So our tuple will be in the form of 2 elements. So the first one will have the value, where let's say the distance part. So we will start it to be the maximum of U32, and let's assume the starting position will be at 0. Next thing what we'll do is we'll iterate through all solutions. So here, let's use a simple iterator in Rust. So for solution, in solutions, we can do it like that. But as we see, actually, we need to store the position for our final solution. So in this case, we will need to actually iterate it and then enumerate it. So enumeration will give us an index. So the solution will be in the form of, let's say, index and the solution value. So I'm using Rust Analyzer. As you can see, it's an extremely powerful tool. Before that, I use just something random or default for VS Code. I highly suggest you everyone to install Rust Analyzer, because dynamically it gives you types and you'll understand way better how your code works and increase your productivity tremendously. It did it for me for sure. Okay. So let's assume now we have our vector. So in solution part, in the first case, will be a vector in the form of 1, 0, 4. So what first thing we need to do is to find the maximum value out of this vector. Rust iterator are very strong, and they can give you this using a small command. So we can use an iterator and use max on that. The code for that will be something like let local max. This can be like solution. We'll do iterator and max. So this will give us the maximum element out of an array. This will return back an option to us, so we'll need to unwrap it. So yeah, kind of we found the max. So let's assume we have 4 here. We started our mean position to max 32, which is 4 billions or something or bigger. Let's write the code that will store our mean position. So let's see. If, for example, our local max is smaller than our mean position at position 0, because we have a tuple, then in this case we'll need to mark our mean position of 0 to be local max, and we need to store mean position of 1, where we store actually the index. It will be our index. So our function needs to return back an usize. So this will be actually mean position of 1 back. We have a little bit of trouble here. So yeah, when you use iterator, actually it will give back a reference to the initial value. So there are 2 options here. Either we can use into, which pretty much will do a copy of our values, but in our case this actually will not work because we received here solutions. So in order to do that, probably we'll need to do into here, but that's not let's say pretty smart way. I guess the simplest way, we can dereference this to be it equal. So actually, yeah, we'll need to do it 2 times. So we'll need to dereference this one 2 times. Okay, what's the problem now? Cannot be dereferenced. Okay, so then let's reference this one 2 times. Okay, found it. Yeah, probably we'll need to do it like this. Okay, and here we'll need to dereference it. So yeah. It's a little bit weird with this reference dereference. You get used to it pretty fast, usually using a Rust analyzer. So this will give us pretty good results. What actually we can do now, we can write a test function to see if this one works well. So let's fastly add a couple. So test, what we'll be testing, we'll test find mean solution. Okay, so let's define a couple of solutions. So we have our vector. Let's write it down. I don't know. It could be 1, 0, 4. This one will be one solution. The second could be 0, 0, 1. And we have another one, for example, 0, 0, 3. Yeah, let's do it like this. We'll put 5 here, we put 3 here, and let's add one more. For example, this one, 0, 0, 1. So I'm expecting the last one to be the index returned by our function here, find mean solutions. So yeah, let's assert that. So find mean solution, we provide a solution, and the expected result will be 0, 1, 2, 3. So we have the 3 part. In order to run this test, actually what we need to do is to mark this as a test. And Rust Analyzer already will give us ability to run it from VS Code. So let's run it. What do we have here? We have a successful test. Awesome. We can continue. Actually, what we can do, we can add another one. So we can play a little bit later on, but overall it works. So maybe what I'll provide you guys, it's a Git repo where you can play with the unit tests, you can add failing tests, and so on. We have a lot of work to do, so let's not waste any time here. Okay, so we wrote down our find mean solution. Next, what we'll need to do is to work and compute the local solution, or compute the solution for each block. I guess what we'll need first to start is to define, as we did on our whiteboard, we have the right solution and the left solution part array. So we'll have left solutions, which will be the structure we defined. If you recall, it will be a vector of tuples like distance of U8s or U32s and the booleans. So that will be our definition. So let's define it. We can initialize them as well. So to initialize them, what we can do, we can define it to be 0, for example, at first, and false. Let's assume we didn't move any distance on the right side, in this case on the left side, and we need to provide how many elements we have. That's the way to initialize a vector in Rust. Okay. So how many it's requirements of len. Okay, so now it's clear. So we initialize the left solutions. We need to initialize as well the right solution. I guess it's not solutions. I guess it will be just solution. So this will be mutable. In this case, we'll need to make sure we mark them as mutable. So if you recall the algorithm, now we need to move on the right side and we need to move on the left side and compute those local solution for each block. Okay, so first let's move on the right side. So let's define, so for example, local index. I'm not sure how we can call it. Maybe it will be local index. In index, because this is our index of the block. So maybe we should call it block index. I don't know. Let it be index for now. Yeah, probably we should call it block index. By the way, in order to rename a variable, every time I use F2, this will automatically rename it everywhere in the function. So it's another hack to move a little bit faster. So we'll define our range. So we have our block indexes, then we have our blocks len, because we need to move to the right side. This will be our local index here for each block. Then inside, what we'll need to do, actually, we'll need to iterate through each requirement. So let's do fastly that. So I know it will be an enumeration. So I'll have it requirement index, and then we'll have the requirement itself. And requirements, we'll iterate them, and then we'll enumerate them. Pretty cool feature of Rust Analyzer, automatically shows us that everything is fine. So this is kind of a helper tool to see if what we're writing down, it's correct stuff. So if you recall, the first thing which we need to do, we need to write down if our requirement, it's 1, it's enabled. Same trouble here. So we have our requirement, which is a reference of U8, and 1 in our case, it's not reference. So simplest way we do it like this: we will reference it. Rust will infer that firstly it was showing it that it's an I32, but now if you can see it, Rust properly inferred it. So if this is enabled, next what we'll need to do actually is to see the value at each block. If the value is 1, So for example, if blocks of local index of requirement index, it's equal 1. And then here we have 2 options. Remember, we have our we need to mark that we found our solution. So our, for example, left solution of requirement index in the position 1, because position 1 for us will keep if we found a value or not, we'll mark it as true. If not, what we'll do, we'll increment our, no, actually this will be a right solution. We already introduced the bug. Good thing we found it out. 0 plus equal 1. And we need to do this only if we didn't found any solution. So else if right solution is not true, so or it's false. That's the same thing. Probably let's do it not true. So yeah, on the position 1, right solution, there is a trouble. What's the problem here? Right solution of requirement index. Yeah, that's the right thing to do. Okay, we wrote the code to move it on the right side. We found out that this part will be kind of reusable. So what we can do, we can generate a function out of it. So I'll show you a cool trick. So you can write down refactor. So you can select first the block part, and then you do refactor, and it will show you extract into function. This is a pretty strong feature. Works in many languages, including the ones which I'm developing into. So I use TypeScript, Node.js on the backend. So I heavily use this feature. So we'll writing down our extract function. Let's call it, I don't know, compute local solution, or in our case, compute requirement solution. Often it has a little bit of troubles inferring the types. In other languages, works much better. In Rust, I feel like you need to play a little bit, but overall, it's a pretty strong feature. So we have some troubles. This cannot be dereferenced. Okay, so we can do it like this. Yeah. But in our other case, this is not mutable, so we need to define it as a mutable. So let's define the right solution as mutable. And we'll need to pass it here also as mutable. As this is a generic function, because we'll reuse for both for right and left, probably we'll need to change it a little bit. So instead of right solution or left solution, let's call it just solution. So again, I'm hitting F2, renaming it, and automatically it was renamed. We pass this by reference, a mutable reference. So this function will mutate the solution value. So usually in other languages, I'm not a very big fan of it. Though Rust has its particular way. So in JavaScript, you heavily leverage, let's say, immutable functions because they are prone to less bugs. So usually it's a smarter way to go. Okay, so let's pass this as a mutable right solution. We use it. What we can do now, we need to traverse on the left. So let's have another local index. In our case, we'll have the following structure. So we have from 0, actually, two block indexes, but in this case we'll need to reverse it because we go downwards, and we'll be calling the same compute function, but in this case instead of right solution we'll use left solution. So we computed our two solutions, left and right. Now what we'll need to do is kind of find the needed one, the right one between these two. So in this case, what we can do, probably we can generate another function, like find the mean local solution. Yeah, naming, as always, it's a tough thing to do, but anyway. So we'll have left solution, and we'll have right solution. So let's find the mean local solution out of it. So I'm expecting this function to return a vector of U32. Let's say we'll generate this stuff. There is an opportunity to refactor it. We can extract this vector of U32 bool in the form of I don't know, maybe it will be a flagged solution, and probably we'll need to find it everywhere and rename it. Yeah, let's move this upwards. Yeah, a little bit too much. So let's keep it here. So everywhere where we'll find this vacuum 32, we can change to our flagged solution. Okay, a hack to find all occurrences from a selection, you use Ctrl-D. So where do we have it? Again, I think we found everything. Do we have anything else? No. Yeah, probably I selected a little bit too much. Let's do again. So you select and then run Ctrl-D, and then you can just call flagged solution everywhere. So it will replace every occurrence of what you found with the flagged solution. So everywhere. So pretty good stuff. Or you can do Ctrl-H and replace. That also works. Okay, so we have our flagged solution, left and right, and now we need to find out the minimum. So specifically for that, I would like to use the power of iterator in Rust, the moment of zipping two iterators. This is a pretty cool feature. Probably I'll move back to our whiteboard and explain it a little bit, because I think that one will be a useful thing to check. Okay, so let's discuss how zipping works in Rust. So this is a very powerful tool to join one or multiple iterators. So let's assume we have the following structure. So we have two vectors, like the following values. The first one will be 1, 2, 3, 4, and 5. And we have the second one with the following values, like let's assume it will be 5, 4, 3, 2, and 1. So there is a possibility in Rust where we can zip these two iterators. Extremely powerful. So if we call this one to be A and the second one to be B, the function will be A iterator, like zip, and we'll be zipping the B.iterator. And in A will become a little bit smarter iterator in the form of a tuple. So we'll have the values from left and right. So we'll have the A value A value and the B value. So for example, for specifically this example, we'll have the following structure. So we'll have 1 and 5, then we'll have 2 and 4. So the sum of the complements will be 6 every time. So I specifically wrote it like this, to the sum of the complements to be 6. But as you can see here, this becomes very helpful in our case, because we'll have two solutions and we'll need kind of to match and find the minimum out of our left and right. So for example, in our case, we'll have something like, let's assume we'll have 1 and true. So for example, for the block 0, then we'll have 0 and true, and we'll have 4 and true. So this will be for the first block, the solution on the right side, but the solution on the left side will be kind of 0 false, 0 false, and 0 false. So these are the solution for the first block. Why? Because on the right side we need to pass pretty much to traverse all the blocks to find this one till the end. But on the left side we don't have anything else, because this is the first block in our chain. So this will be at 0. So this is our initial state. So the end result of our zipping will be something like this tuple, and we'll find out the final solution for each requirement to be the following, like this one because we found it, this one because we found it, this one because we found it. If, for example, there was a case, let's assume we have a case, here we have 1, but here we have 5, and and we found it true on the left side, then we'll need to find the minimum out of these two. So the minimum in this case will be a 1. So let's write down the code for this part to find out the minimum local solution. So we are back on our VS Code. So let's write down the code to find out, let's say, our VEC of U32. So yeah, we have our left solution as we wrote there. We need to zip the right solution, which will be an iterator as well. Then we'll apply a mapping function. Yeah, that's a little bit, let's say, cryptic from one perspective, but nothing out of this world. So let's call it left and right here. I'm pretty sure. Yeah, we received our values, so left and right values, as it was defined on the whiteboard. Now we need to find the minimum out of these two. So as you remember, we have this Boolean flag in order to find out if the solution was found or not. So for example, if left of 1 is true, and let's say right of 1 it's true, then the output of this one will be the minimum between left and right. So it will be left of 0 dot mean of right 0.0. So that will be the first part which we need to mark. If some of them are false, so for example, let's assume the right one is false, so let's check if left one is true, then pretty much we'll return wherever solution we found out when we traverse on the left. So it will be left of 0. And in the end, else if, here we need to write else if. And the final result, let's assume it's right, 0. We have some troubles, yeah, because we need kind of to collect the value and return it back as a vector of 32. Probably it can infer from the output. I think we can keep it like this. We don't need actually to write it down. So let me explain a little bit the things which are going on here. So this part is what we discussed on the whiteboard, the zipping. After that, we use a map function. So map, same as in JavaScript, or pretty much any functional languages, will execute a closure function onto each value of the iterator. So in our case, the iterator becomes a tuple of left and right, because we have two vectors here. If, for example, we had multiple, because you can zip more and more, so you can zip multiple elements, and this can give us multiple of those. But anyway, so we receive the solution from the left, we receive the solution from the right. We check if the flag on the solution on the left was true and the solution on the right was true. Then we need to find out the minimum between these two. Okay. And in the end, what we'll need to do, we return the values, and then we are collecting the values into a vec of U32, which will be passed later on to find mean solution, as we can see it here. Okay, what actually else do we need to do? Looks like everything is done. Do we have any other function to check? Compute solution. We have this compute solution here. We have the right side, we have the left side. Yeah, let's give it a shot. Okay, so this passed. Looks like we are done with our tests. Cargo tests. Yeah, we have 2 tests. All of them are working. I guess that's it with the code. Maybe we can think of refactoring it a little bit, finding proper names. Yeah, let's see, maybe some better names. Here we can see find mean solution. I think we we call this solution multiple times: compute solution, mean solution. It's highly populated word. It's not clear what exactly we're doing. So let's drill again from top down. So we have the optimized blocks. I'm fine with the name. We have compute solution. Maybe we should ignore the word solution. Compute solution. Compute block solution. Compute solution. Compute block solution. Maybe like this we should call it. Compute block solution. Maybe that will be a good name for it. This one, mean local. Mean local. Find mean local solution. Yeah, there is a naming convention. Usually you call each method or function with a verb. Because usually each method does an action, so we should keep this action. I'm not sure exactly why Clippy shows me cargo Clippy. Yeah, we have some things to optimize. Is never used. Yeah, because this we should call it as a public function, but these things are, let's say, not very important for now. Cargo Clippy. There are other things to optimize. Try simplifying it as shown. Left one. Okay, let's see. Cargo suggests us some things. Left one and right one. Does it work like this? Okay, looks like it works. Good. Okay, so we can proceed again with optimization. Change this to the this structure. Okay, let's optimize it as well. So what does it suggest us? Okay. So it asks us to play it like this. I'm fine with that as well. What else do we have? Here, we kind of actually need to do it like that. And here, I guess, will be like this. But this is not a Boolean, so this is why this doesn't work. So we need to explicitly cast the type. Do we have anything else? No, we don't. Okay, so let's review fastly the code. If we remove the comments, how many lines of code do we have? So around 80 lines of code divided in multiple functions. Usually it's a taste, not necessarily important to have it. For me, that's a way to simplify, let's say, the functions in smaller blocks. The algorithm reads a little bit better. Here it's an important thing to know though. When you extract into multiple functions like this, the order of writing them down, it's very important. So for example, if you have a compute block solution, I'm expecting this compute block solution to be exactly next after the optimized blocks, and find mean solution to be after a compute block solution. So for example, this one, I'm expecting it to be a little bit upwards. So structuring the code to be easily found, it's as well very important. In the book Clean Code by Robert C. Martin, he outlines the possibility of indenting them, so kind of in the following form. So for example, a compute block solution and find mean solution will be like this. And then find mean local solution, which needs to be, I guess, after this one. Should be kind of indented. So they are used here. So they should be 4 tabs. So usually in the form of you can see kind of which function is used under each function, so following a tree structure. I personally don't like this approach, so let's keep it simple for now. Okay, so we copied these two. Let's refactor a little bit. So yeah, we have optimized block, we have find mean solution, and then we have compute requirements, and then we can find mean local solution. So everything is in order. Our tests are working. So yeah, thank you guys. If you have any updates, comments, yeah, glad to hear them. Also, will be extremely helpful if you'll press a like button and subscribe. Yeah, have a nice week.